So today I'm going to talk about joint work in progress with Sarah Pennington and Alison Etheridge, which started a few years ago during one of my stays in Oxford. And I guess one of our motivations when we started this was to understand the motion of what we call hybrid zones, and where hybrid zones are interfaces between two regions where different subtypes live and where the subtypes are mutually incompatible. So the simplest example of this is when you have a diploid population with one gene that comes in two alleles, capital A and little a, and where capital A individuals are fitter than capital A, and little a individuals are fitter than capital A, little a. So heterozygous individuals have a disadvantage. And so what you expect to see in these situations is to have separated regions where you have mostly little a individuals and other regions where you have capital A individuals. And at the border between these regions, you will see some heterozygous individuals just because of Mendelian segregation. But you won't see very many of them because they're less fit. And so the contact zone should stay narrow due to selection. And if the two selection coefficients of homozygous individuals against heterozygous individuals are equal, then you expect that the hybrid zone will not move too much. But if one selection coefficient is bigger than the other, then you expect that the fittest type can invade the less fit type. And so the hybrid zone will move here to the right, and capital A allele will invade the population. And so in order to understand this, we can consider this model, so the spatial Lambda-Fleming-Veaux process that was introduced by Barton, Etheridge, and Weber in the year 2000. And the model is as follows. So the population occupies a spatial space RD, and at each location we record the frequency of capital A allele. And so that's the function Wn t of x. Here is the proportion of capital A allele at time t at location x. And the population is going to evolve through a series of reproduction events. And there are going to be three types of reproduction events. And so these reproduction events are drawn according to Poisson point processes. So what this means is that in each spatial square of size L, you pick a neutral reproduction event at a rate proportional to the area of the square, so L to the D. Selective reproduction event in favor of capital A allele at rate S1 times L to the D, and a selective reproduction event in favor of little a allele, little a individuals at rate S2 times L to the D. Right. And so when you look at this, you see that the definition does not depend on capital L, and this is what Poisson point processes are. And so at each time we have these events, we pick a center X, and we have a fixed radius R that is deterministic and fixed throughout. And each reproduction event is going to affect a ball of center X and radius R. And so during these reproduction events, some individual is going to reproduce and replace some individuals in the population. And so the simplest case is for neutral reproduction events. So if such an event takes place in the ball of center X and radius R, we're going to pick an individual to reproduce. And since individuals are diploid, we're going to pick two types. And I'm going to pick two locations uniformly in the ball, and a type at each location according to the proportions right before the reproduction event. And this gives me a genotype, K1, K2. And this genotype is going to produce some offspring. And I'm going to kill a fraction U of the individuals in the ball and replace them with the offspring of this individual. And so the new allele frequency, so the new frequency of capital A allele right after the reproduction event is 1 minus u times the frequency just before the event, plus u times this thing, which is just counting 1 for homozygous individuals and 1/2 for heterozygous individuals. And on top of that, we have selective reproduction events which select in favor of homozygous individuals. So in order to select, to have natural selection, we're going to pick 2 individuals, and so 2 individuals is 4 alleles. So you pick 4 independent locations. At each location, you pick a type according to the proportions right before the event. This gives you 2 genotypes, K1, K2, and K3, K4. And if one of them is the one that you're trying to select for, then this guy reproduces. So if one of them is XX, where XX is either capital A or little a, depending on the kind of selective reproduction event, this guy reproduces, and if none of them is the one that you're looking for, then you just pick one at random. And you have the same rule for updating the allele frequency after the reproduction event. So you kill a fraction u of the individuals inside the ball, and you replace them with offspring of the parent that you've just chosen. Okay, and let's see now if I can do this. Copier dans le presse-papier, yes. So this is what the model looks like if I start with a sharp interface at the beginning. So I have a lot of reproduction events falling down at a constant rate, and each time I pick individuals according to the rules that I just explained. And I have this wiggly interface, a bit fuzzy, that is developing a long time. And if I wait long enough, I will see the capital A allele frequency invading, so everything is going to be red after a long time. Okay. Yes. Okay, how do I? Yes. And so, okay, so this model is a bit hard to analyze. So we're going to take scaling limits in order to understand what is happening. And the way we take these limits is we assume that the parameter u, so the fraction of individuals that we reproduce at each event, is small. So un is going to be u over n, and the selection coefficients are also going to be small. Over the delta n squared, where delta n is going to be some parameter going to 0. And we are going to rescale space and time in the following way. So I zoom out of the process, so I look at spatial scales of order 1 over delta n, and I speed up time by a factor n over delta n squared. And from Etheridge, Weber, and Yu, 2020, you can see that if this quantity here tends to infinity, then the stochastic process converges to a deterministic limit ft, which is given as the solution of this PDE here, where you see the effect of dispersal here through a Laplacian, and the effect of selection here through this reaction term here. And if you look at it closely, you will see that it's negative when f is small, is close to 0, and it's positive when f is larger than some threshold. So it's a bistable reaction diffusion equation, and we know a lot about these equations. And okay, keep in mind that something had to go to infinity in order to get this deterministic limit. Right, so these deterministic equations are well studied, so for simplicity we can just consider the one-dimensional case for now. And in the case where f of p is p1 minus p, it's the famous Fischer, Kolmogorov, Petrovsky, and Piskunov equation, where we know that there exist traveling waves solutions. So these solutions are special solutions of the form m of x minus ct. So it's a fixed profile that is moving at a constant speed at speed c. And so these guys exist for any c larger than some c star that is twice square root of s. And actually, if you start from a compactly supported or a heaviside initial condition, then your solution converges to the front that is moving at the minimal speed c star with a weird spatial shift here that I'm not going to talk about. And for the case that we're interested in, that is the bistable case, f of p is of this form. And in this case, we also know that there is traveling wave solutions. In fact, there is a unique profile, m, and so a unique speed. And any initial solution that is reasonably like a front is going to converge quite quickly, so in fact exponentially quickly, to this stationary profile that is moving at constant speed c. And here there is no correction term here to the speed. Okay, so this is what happens in a deterministic setting, and we want to understand what happens in a stochastic model, so a bit before we take the limits. And the model is still too hard to analyze, so we're going to consider a different scaling than the one before. So I still assume a small impact parameter and small selection coefficients, and I still look at the process on the same spatial scales and time scales, but now we're going to assume that this quantity is equal to 1 instead of going to infinity. And you can only do that if you're in one spatial dimension. Right? If you look at this, delta n is going to 0, n is going to infinity, so you need d to be equal to 1 in order to have this thing possibly equal to 1. And what happens if you do this is that the stochastic model converges to a stochastic limit p that is given as the solution to this stochastic PDE here, where you still see the same terms as in the deterministic PDE, so the dispersal and the reaction term, but you now have a noise term in addition, which looks like a right Fischer noise at each spatial location, essentially. And so I can show what this guy looks like. So now we're just in one special dimension, so I'm just plotting the frequency of capital A allele as time goes by. And so you see that it's, so I've started from just capital A allele to the left of some point. And you see that this wiggly interface develops, and the solution is stuck at 0 over here and stuck at 1 over here, and is doing some strange thing. And is, if you wait, you see that it's moving to the right at some speed. Okay. So this equation we have some hope of understanding, and in fact we're still not going to understand this equation precisely, but a small noise limit of this equation. So a bit of gymnastic now. Suppose I'm now back in a setting where I converge to the deterministic limit, so this guy is going to infinity. So my spatial lambda-Fleming-Vieux process is doing some fluctuations around the deterministic limit, and we're going to cross our fingers and hope that these fluctuations are roughly the same as the fluctuations of the SPDE, where I put a small noise term. Okay, and if you do the calculations and you compute the mean and the variance, you can convince yourself that this is the right scaling to consider. And so we are going to now completely forget about the original model and just work with this Vn, or actually this V epsilon, where I've just dropped all the constants in front of the Laplacian and in front of the noise. And so what we have is a dispersal reaction term and a small noise term, where epsilon is going to go to 0, and we're going to try to understand what this guy does. Okay. A short word on what happens in the Fischer KPP case. So if I take f of p equals p1 minus p, this has been very well studied. And so Miller and Soros in 1995 showed that there exists a stationary, in distribution, it's a random front. And if you look at the position of this front at time t, you divide this position by t, and you let t tend to infinity. This converges to some C epsilon. So this C epsilon is the asymptotic speed of this random front. And Okay, there are a lot of related works on also related models and similar equations. And Brunet and Derrida in 1997 conjectured something that was proved later in Müller, Mitnick, and Kastel, that this C epsilon, when epsilon goes to 0, behaves as follows. The leading order term is twice square root of S, and you have a correction term, first order correction term, that is minus constant over log epsilon squared, plus some smaller order terms. Okay, so this twice square root of S is not surprising because it's the speed of the deterministic wave. So you expect that when epsilon goes to 0, this speed should converge to the speed of the deterministic wave. So this is not surprising. This log epsilon squared is a bit more surprising. It's a very big correction. So it's going to the deterministic speed, but very slowly as epsilon goes to 0. So the noise has a dramatic effect on the propagation of the front. Okay. But we are not in a Fischer KPP case. We are in a nicer world of pushed waves, where so I'm going to rewrite now the reaction term f as some mean selection coefficient s here in front of everything, and I'm going to split the reaction term in two terms. So one is going to be a symmetric term, which means that this guy is not favoring one type over the other. And I have plus alpha p1 minus p, so this guy measures the strength of the selection in favor of the capital A allele. So alpha is S1 minus S2 over S1 plus S2, so you see that if S1 equals S2, then alpha equals 0. And actually, so alpha equals 0 is the red curve here, right? So you can see that it's perfectly symmetric with respect to this point here, and the area under the curve is 0, so this guy does not favor anyone. And when alpha is a bit positive, you have this green curve here, so this is for 1/2, where the allele frequency decreases when it's small, but it increases when it's big. And at alpha equals 1 is the point where you lose this property of decreasing at small frequencies. You always increase, but you don't increase as fast near 0 as at some point here. Okay. What do we know about the deterministic equation? In this case, as I've said before, there is a traveling wave solution. It's unique, and this holds for as long as alpha is less than 2. And actually, the deterministic profile is explicit and does not depend on alpha, and the speed of the wave is proportional to alpha. Right. There is previous work on these equations, slightly related as PDE, where we have the same deterministic part and a slightly different noise term in the case where alpha equals 0. So in a perfectly symmetric case where the interface is just centered around 0 and with a different noise term, these two papers in 1995 independently proved that if you look at the solution to the SPDE and you speed up time by a factor of 1 over epsilon, then this guy looks like the deterministic profile, M, but shifted by a random amount psi epsilon. And this psi epsilon converges in distribution as epsilon goes to 0 to a process psi t that is given as the solution to this simple SDE here. Yes?
There is no epsilon anymore in the SPDE.
Yes, that's right. There's a square root of epsilon here that is missing. Thank you. Yes?
Why does the noise term has symmetry?
So,
How can you explain that the noise term has the first term in the noise term? Is it pushing the noise towards a certain direction?
This guy here, so the A of xt grad x of A of xt. Yeah, this is a drift term for the SD. So if your noise can affect where your wave can end up.
But it's okay. The big difference with equation that the coefficient for dw doesn't depend on v here.
Yes, yes. So the two equations are quite different, but actually the techniques that we use are very close to the techniques of Funaki. And so this is the thing that we're in the process of finishing to prove. And so this is our noise term, and we have also a different reaction term. So we've added a bit of asymmetry in favor of one type. And what we can show is that for alpha between 0 and 1, if you look at the stochastic model but shifted in the deterministic moving frame, so you look at its position relative to the deterministic wave, and you speed up time by a factor of 1 over epsilon, then again this guy looks like the profile of the deterministic wave shifted by a random amount psi epsilon. And this psi epsilon converges in distribution to a process psi of t, which is just a Brownian motion with negative drift. So
Mu and sigma are given by.
I will show sigma and a bit of mu in the next slide. So if you just take this result for now and look at what it should mean. So if you look at v epsilon t, that means that it's roughly the deterministic profile at position ct minus mu epsilon plus a Gaussian term of variance of order square root of epsilon. So this is very different from what we had for the Fischer KPP equation, where instead, so okay, I haven't taken the limit as t goes to infinity here, but if you believe that you can exchange the limits, then the asymptotic speed of this guy should be c minus mu epsilon. And so the correction to the velocity term is much smaller than in the Fischer KPP case. And the intuitive reason for that is that in a Fischer KPP equation, the growth of the wave is driven by the individuals that are far ahead in the front, where the noise is stronger, and where actually the SPDE is compactly supported, where the deterministic wave propagates instantly to infinity.
So here alpha in 0 means that the equilibrium is bistable?
Yes, exactly. So
There's
it's exactly bistable. So it's always negative near 0 and positive above a certain threshold. And so this means that here the individuals that are far ahead in the front are actually subcritical. So they're dying anyway, and they're not contributing to the growth of the front. The front is only driven by the growth of individuals that are a bit in the bulk. And this is why the noise has a less dramatic effect in this case. And things become more tractable, actually, and so we can even get the variance of the position of the front. Okay, so here is the expression for sigma squared. So it's given fairly explicitly in terms of the shape of the deterministic wave profile, in terms of these integrals where you have these exponential weights appearing here. And mu is a bit more nasty to write, but we also have an explicit expression. And so these expressions were given in Bezu, Halacek, and Korolev, who studied these kinds of stochastic traveling waves. And so we essentially proved what they stated in this paper. And this is the shape of the function sigma squared as a function of alpha here, where alpha equals 1 is here. So you see that between 0 and 1 it's quite well behaved, and it diverges at alpha equals 3/2. And you can see this analytically from the expression that this integral is finite for any alpha less than 3/2. Okay. Very quickly, I'm going to try to explain maybe not the proof, but the philosophy behind the proof. And it's based on, so it's based on the proof of Funaki, which itself is based on a previous paper by Katzenberger, who was a student with Tom Kurtz, and who looked at a finite dimensional setting. So suppose you have this x epsilon here that is doing some diffusion in RD, where you have a order 1 drift term and a small order noise term. And the assumption that we make on the B is that the deterministic flow associated to B, so this is this phi t of x, right? So if phi t of x is the function of time that gives the solution to the ODE started at x. And let's assume that B is such that if I start from any point x, then phi t of x converges to something that I'm going to call m zeta of x, and where this guy belongs to a one parameter manifold, submanifold. So this is the picture that I've drawn here, right? So B is pushing you onto this somewhat linear manifold here. And so if you start close to the manifold, you expect that your diffusion is going to stay close to the manifold because you have a strong forcing term that is competing with a small noise term. But the fluctuations in the direction of the manifold are not suppressed. And so you can still see them on the right time scale. Okay, a bit of stochastic calculus. The idea in the proof of Katzenberger here is to use this coordinate here, this zeta. So remember what I assumed here. So the flow converges to a point on the manifold, and zeta is the coordinate along the manifold of where you're going to end up if you start in x. So it's the projection along the deterministic flow on the manifold. And so we can define psi epsilon to be this projection of the stochastic process where I've sped up time by a factor of epsilon. And I can apply Ito's formula, provided that zeta is nice enough. And I have three terms in this Ito formula. The first term here is fairly nasty. It has a 1 over epsilon in the front, but it comes from the deterministic flow in the SDE. The second term is a martingale term. It comes from the noise. And this guy is the Ito correction term. And so both these terms are now order 1 because I've sped up time the right way. And I have this nasty term in the front that I would like to get rid of. And in fact, we can get rid of it because we've chosen the right projection on the manifold, essentially. So zeta of phi t of x is constant because zeta is actually the limit of phi t of x. And so if I differentiate this guy, I get 0, but I also get this expression here. And so if you let t tend to 0 in this expression, you get that actually the gradient of the projection is orthogonal to the flow, which means that this guy actually is not there. It's equal to 0. So the bad guy is gone. And we only have order 1 terms. And so now we're in a good place. And if we show that this psi epsilon is always close to its projection onto the manifold, we can show essentially the convergence of this psi epsilon to a stochastic differential equation, to the solution to this stochastic differential equation written here, which you can express in terms of the derivatives of the projection onto the manifold. So this is the idea in the nice finite dimensional setting. And what Funaki did is that he transposed essentially these ideas to the infinite dimensional setting of the stochastic partial differential equation. And so this is just a slide to convince you that there is an analogy. So instead of x epsilon t, we have this v epsilon t that we've shifted to be in a deterministic moving frame. And now the manifold of fixed point for the deterministic flow is just the set of deterministic profiles M with all the possible shifts, all the possible real shifts. And the deterministic flow associated to the PDE the deterministic part in the equation is now a PDE. And we have this term that comes from the fact that we're looking in the moving frame. And this guy we know from previous results that I stated before, that phi t of x converges to one of these guys for any v nice enough. Okay. And so you can define the analog of the zeta of x that we had before as zeta of v, which is the coordinate along the manifold of where you're going to end up if you follow the deterministic flow. And this allows you to write down the mean and variance of this guy. And what you end up with is something that looks like this, where xion of t has two terms, because so there's a third term that I haven't written that was equal to 0 because of the same cancellation as before. And so we have a martingale term here that is going to be essentially a Brownian motion, and we're going to compute its variance easily, and the Ito correction term is going to give you the drift. And so if you look at the first term here, you can sort of guess where the expression for sigma came from here. So we had an integral against white noise of square root of n1 minus m, so this guy gives us this thing, and we have the other terms that come from the derivative of the projection onto the manifold. Okay, and so this is just to sum up fairly quickly. So basically what we've covered here is the case where alpha is between 0 and 1, so it's the bistable case. And we saw that the expression for sigma squared diverges near 3/2. So actually, we sort of hoped that when we started that we would be able to prove things for alpha up to 3/2, but for very technical reasons, things become less well behaved between 1 and 3/2. And so for now, it's just a conjecture. And what happens, okay, beyond 2, it becomes a pooled front. And so the correction term is going to be very nasty. And between 3/2 and 2, what happens is still a bit mysterious. Okay, and I stop here.
Okay, we're quite over time, so maybe one quick question before we go to the next.
So, is there an intuition for the manifold where the deterministic dynamics vanish in your PDE case? Is there an intuition for what it is? Is it the front?
Yeah, exactly. The manifold is the set of fronts with all the possible shifts. And so the neighborhood of the manifold is a bit more tricky.
Okay, so thanks again.